This is difference. I want to welcome everyone to today's workshop. This is Difference in Differences. This is a workshop sponsored by the Population Dynamics and Health Program here at the Institute for Social Research at the University of Michigan, Ann Arbor. So I'll say a little bit more about PDHP here in a second. But my name is Brady West. I'm the director of the Scientific and Technical Core of PDHP. And again, I want to extend a warm welcome to everyone for joining today. We're expecting a very large audience, so people are still joining, and I'm sure people will continue to join over the next couple minutes or so. But I wanted to get going with some preliminaries today. So first of all, a little bit about the Population Dynamics and Health program here at ISR. This is basically a research infrastructure unit here at the University of Michigan Population Studies Center. And we focus on supporting a variety of researchers, both internal to U of M and external, who are working within the field of population science. And our goal is really to promote scientific innovation and help people to develop research ideas and proposals and make sure that the best possible research on population science is getting funded. So we provide a variety of resources and services, and this is one of the services that we offer, is this free workshop series, and we're delighted to have the workshop today for everyone. PDHP is defined by three cores. We have an administrative core, a development core, and the scientific and technical core. And the scientific and technical core is what offers the workshops of the type that you're going to see today. But again, PDHP provides a variety of services. We offer a small grant mechanism. So periodically we'll have calls for small grants, where you can write applications to do small research projects or get seed grants to get research projects going. That's one possible option. We do have an option to become an affiliate of the Population Dynamics and Health Program. So you can also visit our website to look into that option as well. The website is pdhp.isr.umich.edu. Okay, so we'll communicate that with everybody. But that's what you see on your screen right now. I'm just navigating through the PDHP website here. So you see a variety of options for these small grants, and we prioritize funding research that's within the scope of the Population Dynamics branch of NICHD at NIH. And I do want to acknowledge funding for PDHP coming from the NICHD P2C PRIP program, which again provides support for center grants in population studies. So this entire workshop and the ability to put these workshops on for free is being sponsored by NICHD and this P2C mechanism. So we do want to acknowledge that support, as we are very grateful for that. So as far as workshops go, the slides, the materials, and the recording of today's workshop will eventually be posted on the PDHP website. And you can see there's a link here to a YouTube playlist for the Institute for Social Research. And what we're trying to do right now is post all of the PDHP workshops that have been recorded on this YouTube site here. So thus far, we've posted 2 of our recent workshops on applied multi-level modeling and on multiple imputation and practice. We're going to try to break our workshops up into segments so they're a little bit easier to digest. But eventually, all of our workshops, including today's workshop on difference and differences, are going to be posted to this ISR YouTube playlist. So you can certainly subscribe to this playlist, and then you'll get notification anytime new recordings of the workshops are available. So we do want to make all the materials and the recording from the workshop today available on that site, and eventually that will be posted. You'll also be receiving by email a feedback form, a link to a feedback form that allows you to provide some feedback on today's workshop. Welcome to share thoughts, ideas, provide Pedro with some feedback on the material. We do take those feedback forms very seriously. So if you do get a chance, please remember to provide some feedback on that form when you receive it via email. I also want to mention that PDHP does provide research services as part of the STC. So we often enter into contractual agreements with both internal and external clientele. Maybe you have some funding available for data analysis, or you need some help putting together a proposal, something like that. We do have that level of service available. And if you're interested, you can contact Paul Schultz, who's also today with us today on our panelist. He's our lead statistician within PDHP and also a consulting data scientist. He manages the day-to-day operations of the PDHP, and you can get in touch with Paul if you'd like to explore that possibility of setting up a contract where we could assist you with your own research. For affiliates, we also provide consulting. So if you have a question about a project or you want to discuss a particular research design, Paul, myself, and our team, we can provide you with consulting services, but we do want you to apply to be an affiliate first in order to access that free service. Okay, so that said, again, you can visit the PDHP website to see this link to the YouTube playlist and to access the materials after the workshop concludes today. So that said, I would like to introduce our very special guest who is going to be presenting this workshop today. Pedro H.C. Santana is a principal researcher at Microsoft. He's also been on leave from Vanderbilt for the last 2 years, where he is an assistant professor of economics. Pedro is an econometrician and works in causal inference and semi and non-parametric methods. Much of his recent work aims to develop, better understand, and further improve difference in differences methods, which is the topic of today's workshop. In fact, Pedro is among the most impactful researchers working on difference in differences methods. His work has been cited nearly 3,000 times on this topic. So again, very special guest today, very fortunate to have him here. The econometric methods that he's developed with Brantley Calloway in their paper, Difference in Differences with Multiple Time Periods, is really becoming the standard in many circles, and you'll learn more about that today as well. Pedro is published in top economic journals, including Econometrica, the Journal of Econometrics, and the Journal of Business and Economic Statistics. Pedro has also co-authored several open source R packages for difference in differences methods, giving him firsthand experience on the theory and practice of these modern econometric techniques. He received his BA in economics from IMEC-MG in Brazil in 2009, his PhD in economics at Universidad Carlos III de Madrid in Spain in 2015, and he's a recipient of the 2016 Arnold Zellner Thesis Award in Econometrics and Statistics, which is awarded by the American Statistical Association. So again, very special guest today. And at this point, I'm going to turn it over to Pedro, and he'll start to share his materials and introduce the overall workshop. So Pedro, floor is all yours.
Now, thank you, Paul. Thank you, Brady as well, for the great introduction. And thanks everybody for being here early in the morning for some, late in the evening for others. I mean, it always blows my mind to see so many people watching these workshops live. And it's a great honor that you trust me with your time. And let's see how much I can give it back after all that. So today I'm going to be talking about differences and difference methods. It's going to be an overall lecture. I'm going to try to cover a lot of material in 4 hours, right? And my principle is that we're going to start things from basics, and we're going to build from the very basics, little by little, until we cover some more advanced materials. That is to say, for those of you who are already oh, I'm already familiar with diff-in-diff, I have used this a lot, I'm on here only for the advanced material. I'll ask you to sit tight. Let's build on the intuition. Let's build on the basics so we can get everybody on board. And once everybody's speaking the same language, we're going to go very fast to that kind of material, right? So that kind of advanced material, so we can have firsthand experiences, not only on the theory, but also in the practice. Today's lecture is going to have 2 exercises that I'm going to cover in detail, right? I'm going to use RStudio and R to do all my exercises. Having said that, we're also going to post Stata, do files, replication files that we can do exactly the same exercise in Stata. And all this material is going to be available at the PDHP website, right? If you don't know what is the website, take a look in the Q&A. There is a link in the Q&A for having access to that. I'm not 100% sure if the material is there already, but it's going to be there very soon. So sit patient with me. Right. So again, thank you everybody for having me, and let's move these things along to see how further we can go. So we're all here today to learn about difference and difference, right? We're all here, the title of the workshop, you see my name, it's very common to associate with difference and difference. The first question that I usually want everybody to ask is, why? Why are you going to spend 4 hours talking about differences and differences? What is the appeal of this? Why we even care? And one way to analyze, to tackle this type of question is to see like what has been going on in the last couple of years. So like, I don't know, a couple. When I say couple, I mean 30 years in terms of popularity of different research designs or with respect to different like observational causal inference tools. And to tackle this question, to motivate the importance of differences and differences, there is this extremely nice paper by Curry, Clive, and Zewers in 2020, like AAPNP. And what this paper does, it is like they run a natural language processing in every single empirical paper in top 5 economic journals or in the empirical NBR working paper series. And they search for certain terms that characterize different like econometric methods. So in this is kind of like figure 4 from their paper. And figure 4 here reports like 4 different words: differences and differences, regression discontinuity, event study, and bunching. In the paper, they have other figures, this like also documenting like experimental data, instrumental variables, and other things. But what I want to take a look in this picture is to see like, well, in the last 30 years or so, or 40 years or so, the popularity of all these different methods has been growing over time. And that's fine, that's expected, because that's like nowadays we have access to better computers, we have higher computational power, we have access to better and more informative data, right? So this is kind of like credit to the like credibility revolution, or essentially like the inflow of better data and emphasis on what type of variation in the data we are exploring to answer different policy questions or causal questions in more general. So the trend expected, but let me call your attention for the levels, right? Because I mean, things growing over time, we know this is expected in many different methods. But the levels is something that is very interesting for me, because in the last 20 years, we have seen a lot of developments in regression discontinuity designs in RDD, especially in terms of econometrics. Right? So panel B here, we see like, well, in the last 20 years, I mean, you have heard about RDD, bandwidth selection, data-driven selection, multiple cutoffs, and indeed, like around 10% of the NBR working papers, empirical working papers, like mention the word RDD, regression discontinuity. Among the top 5 economic journals, around 7%, right? Now let's shift these things to differences and differences. Difference and difference is at least twice as popular as RDD, right? So around 2017 here, we have around 22% of papers mentioning the word differences and differences in the NBR, in the universe of NBR empirical papers, and around 15% in top 5 economic journals who have some empirical session. Event study is less popular. I mean, the methods are more frequent, bunching as well. But I mean, what is striking to me is like essentially 1/4 of empirical papers, the NBR working paper series, mention diff-in-diff. And why I'm stressing this so much? Because this is to say, well, we are here. We're going to spend 4 hours talking about difference and difference because of that. Right? Because we want to have a better understanding of a topic that is so popular that is essentially the bread and butter of empirical research. So during these 4 hours, we're going to go deep into these difference and difference topics. We're going to talk about what they are, how they differ, like how the complication that it comes. We're going to talk about like variation of difference and difference implementations, what happens when you have variation treatment timing, and essentially because this is arguably the most popular method when you have observational data. So this is popular, and we agree. That's why we're going to spend on this. I usually do not really like that kind of explanation, right? Oh, we're going to do this because it's popular. Oh, we're going to jump on the bandwagon and then everything is fine. Well, that can be sometimes kind of quote unquote overselling. So in order to motivate the appeal of differences and differences, let's give one step back and say, well, if I'm not, instead of differences and differences, what can I actually use in terms of estimation strategy to uncover causal effects? And here I'm going to emphasize 2 alternatives. One, what I'm going to call lookalike analysis, or an analysis based on outcome equations, on regression models, or unconfounders. we're going to have another analysis that is based on pre versus post periods. Then we're going to talk about differences. All this discussion is going to make more sense if you do not have access to experimental data, right? So like say, look, I don't have an experiment. I'm not a randomized experiment. Therefore, I cannot just use simple comparison of means to uncover the causal effect of interest. Because of that, I'm going to look for alternative tools. In my experience in the tech industry and also my experience in academia, highlights that two of these techniques are perhaps the most popular one. Let's dig with observational data, talk about lookalike analysis, or we're going to rely on regression techniques, reweighting techniques, or if you want to go fancy, we're going to rely on what is called double machine learning or data-driven adaptive methods. All these different names or different techniques means that we're going to assume that we have a very rich data set, and in this data set, everything that matters for treatment selection and the outcome of interest, it's accounted for. Think about this. If I want to model earnings, right, and I have my treatment is training, I'm going to have in my data set everything that affects the decision to enroll into training, right? Motivation, like I don't know, like expectations of future earnings, macroeconomic conditions, education, age, you name it, right? Everything that affects the decision to join training and also my future earnings. So everything that affects these both processes, right? We're going to call this are confounding variables, a variable that jointly determine the outcome of interest and treatment selection, are completely accounted for, right? This is in general is a strong assumption because, for example, motivation. I have never seen a data set when I can actually like reliably quantify motivation, right, in the decision process. And therefore, because motivation doesn't lie in my data set, I'm always going to be like, well, you know, do I really trust the analysis, right? Do I really trust the output of these procedures? Can I actually attach a causal interpretation to it? And that's always kind of like the elephant in the room when you rely on unconfoundedness type of methods, right? Essentially, when I have to rule out that units can select into treatment based on unobservables. And unobservables here is a term that is everything that does not lie in my current data set. Say, fine, I'm going to have these procedures, I'm going to have these potential issues. So sometimes it gives, these methods gives a good pass, a good first order approximation, but it's always tricky to see, like, do I actually trust my output results? Then say, fine, if I do not want to do, if I'm worried about selection on unobservables, what else can I do, right? Well, I can rely on a pre versus post type of analysis, which means I'm going to get units who are eventually exposed to treatment. In my previous example, we're going to have like workers who actually enroll into training, right? And we're going to analyze these workers before they enroll to training and after they enroll into training. And then you're going to say like, well, all the difference between the after training versus before training in terms of earnings can be credited to the training itself, because I'm comparing the same individual before and after the treatment exposure. So this difference is going to be credited to the treatment of interest. This usually works very well when I have short window of time, meaning when I have like the pre versus post are very nearby. So I don't know, say like 1 week before training and 1 week after training. But if you look at this kind of example, nothing going to really happen in the short run in this particular case, right? So when the short run analysis, it is not really the main focus of the policy question, this pre versus post can be tricky, right? Because it's going to not, I mean, if I take long differences, right? If the pre, it's 1 year before, and the post is 1-2 years after the training, right? Things in between these time periods may have changed. The economy may get into a recession, right? We have different macroeconomic shocks. So, and these shocks can affect different like groups differently potentially. So in general, right, pre versus post analysis, not going to be able to account for time trends in the outcomes. So it's, again, it's kind of a complicated matter to credit the difference between before and after only to the policy, right? So what do we want? We want to filter out what is the policy effect, the causal effect, and what is everything else. So these two types of analysis are alternatives to difference and differences, but they have clear kind of complications. So the way I view differences and difference methods, it is like we're gonna merge the two of them, right? It's as if like unconfoundedness and pre versus post get married and have a baby, and the baby is gonna be the difference and difference analysis. What do I mean by that? We're gonna exploit like before versus after type of analysis, and on top of that, we're gonna exploit variation of treatment exposure across groups. So we're going to compare treated versus untreated units at the same time. So the idea is to combine unconfoundedness and pre and post, right, informally speaking, to avoid their limitations. By doing that, differences and differences is going to allow for time trends and also going to allow for selection on unobservables, right? This is, for me, the reason why difference and difference methods is so popular. Right? When you go back to these slides here on the popularity in slide 1, right? Essentially allowing for time trends and allowing for selection on observables partially explains why we have this big boom and the big popularity of difference and difference methods. As any causal, I have to give some highlights here and some words of caution as well. Any causal inference method, it is not magical. We're going to rely on assumptions, right? So here we also want to rely on assumptions in difference and differences. And the main assumption we want to rely on, it is that if treatment did not happen, so in a word, in the absence of treatment, right, we're going to assume that the evolution of the outcomes among treated units and untreated units would have evolved in parallel. This is the so-called parallel trend assumption. And we're going to talk a lot about parallel trend assumption today as well. But I want to tell you, like, we're going to allow for time trends. We're going to allow for selection of observers as long as we have this kind of parallel trend assumption. In practice, it is very important to take a look in your real application to better understand just how units enroll into treatment, how select into treatment, and then argue why this assumption is plausible or not, right? We're going to briefly touch on this matter today. But I want to emphasize that like this is not black magic, right? As any causal inference methods, we're going to rely on assumptions and data. And this is the key here. So this is all fine, right? Difference and difference is very simple. And the description that I have given is, I hope it's very intuitive. But in the last couple of years, right? This is perhaps why all of you are here today, like either live or watching us in the recording, right? We have seen this big boom on difference and difference methods. Many of the techniques we use to trust and rely in our empirical analysis have been put under scrutiny, and we start questioning its validity, right? Is this method actually doing what it's supposed to do? Can I actually trust the output of this regression technique? And the econometric techniques involved in diff-in-diff exploded. And I know I'm partial to be like, you can blame me a bit of that. You can blame some of my co-authors, several of my friends, right? Doing this. And I understand that right now you have this kind of like butterfly in your stomach that is kind of complicated. You feel like unsure. And my main goal today is to say, let's hold hands, let's walk through the basics, and let's get everybody on board, because all these new advances can be easily explained using simple comparison of means. Essentially, we can motivate a lot of advances by just doing like simple comparison of means, but in a more guided way. So because
I'm sorry to interrupt
yes.
you. We've got one question I think you want to address right away. So
Yes.
The question is this: selection on unobservables is only allowed as long as unobservables are constant over time. Is that correct?
So classically speaking, it is correct, right? So we're going to allow for unobservables that do not affect the time trend differentially, right? So I mean, Essentially, we cannot allow for unrestricted unobservables enter into the model. We're going to have to put some restrictions on how this unobservable enter into the model, right? We can allow for selection on time-varying unobservables, but it has to be some type of particular type of unobservables that are time-varying that can affect both of them. So the usual way we can motivate differences and differences, it is time, like unobservables are time invariant and enter into the model additively. That's for sure like allowed. Now, if you allow for time-varying unobservables, is parallel trends still compatible with that type of question? The answer is depends, right? And I want to point you to this paper by Dalia Gannon, myself, and Caspar Ulrich, when we actually trying to see try to answer this question in particular. What type of selection models are compatible with parallel trends? So what type of like time-varying unobservables can incorporate into the model such that parallel trends is still valid? So in this paper, we dig into this question, and the answer is like, yes, we can allow some, but we cannot allow all. So we're going to have to put some restrictions over there to further dig. So I hope I have answered your question. It's not a like slam dunk answer, but at least it's an answer that like gives you a starting point to dig through more on that. So good. So this big boom on differences and differences, right? Me, John, Alisa Belinsky, John Roth, Alisa Belinsky, and John Paul, seeing all this like emerging of this literature, and with a lot of sympathy and understanding of our friends in empirical researchers, we say, well, let's try to make things simpler, right? So let's try to summarize this literature and what has been going on by then to 2021, right? And provide concrete recommendations for practitioners on what you should do. So in this paper, what we cover the canonical diff-in-diff setup. We're going to cover that today as well. We cover variation treatment timing situations. So meaning treatment selections, like we're going to difference and difference where units select into treatment in different points in time, right? So not everybody is treated today versus never. Some of units are treated today, some of them are treated like in 10 days from today, 20 days from today, so on and so forth. So I do allow units to sort into treatment in different points in time. There is a lot of the literature who talks about like problems with the two-way fixed effects regression methods on that and how to solve it. We're also going to cover some of this today. In the paper as well, we cover like how to relax parallel trends and how to do inference when I have not many clusters, very few clusters. These two topics, most likely, we're not going to have time to talk today. But again, feel free to take a look in the paper. We have a lot of details and concrete recommendations for those. This was written in 2021. But since then, the difference and differences literature did not stop, right? So since then, the literature kept evolving because we see more people talking, more people interested in diff-in-diff, right? So since we wrote that review, many new topics have emerged. Here is just a sample of these new topics. So what happens when I have a continuous treatment? Like what happens, how much should I trust my diff-in-diff in terms of functional form restrictions? What types of selection models are compatible with parallel trends? How can I combine machine learning and diff-in-diff? What if I do not have a single treatment, but I have several treatments taking place? All of these are new questions that are not addressed in our review, right? But this is just to emphasize that this is very active literature, and all of you who are listening, right? There are still many more things to be done, right? So don't get discouraged and say, oh, this is already mature literature. It's definitely not the case. There are many more topics that is worth attention, and I'm happy to chat offline with several of you if you want to engage in those discussions. Today, due to the time constraint, I'm going to cover a very limited amount of these materials. So I'm going to talk about canonical diff-in-diff, which is the textbook diff-in-diff situation, 2 periods and 2 groups. And I'm going to do that because that's going to provide the foundations to do extensions. Once we understand the 2 periods, 2 group diff-in-diff very well, it's very easy to see how this recent advances deviate from the canonical model. After that, I'm going to talk about what happens in staggered treatment timing. I'm going to talk about difference in different situations when units are exposed to the treatment in different points in time. And here I'm going to stress two main points. The first main point is going to be about potential limitations of classical tools, such as two-way fixed effects regressions, right? And this is going to cover a lot of material. And this is the groundbreaking work of Andrew Goodman-Bacon, who, by the way, was a fellow of the center, right, when he was a PhD student at Michigan, right? So this is like, this diff-in-diff words go all the way when Bacon was a student at Michigan, right? So it's for me, it's a big pleasure to be here today to kind of like, oh, when everything started, we can come back again and let's wrap this over. So these problems of diff-in-diff, we're going to talk about the Goodman-Bacon paper, who has nearly 3,000 citations as of today. The Charles-Martin and Dufay, right, the AER paper also talks about this. Sun and Abraham also talks about this. So we're going to discuss these three different papers, how their like characterization of the negative weighting problems, of the problems of two-way fixed effects regressions emerge. Because I do not like to be a nagger, right? I don't like sad papers. I like happy papers. Meaning, it's very easy for us to point out problems. We're not going to stop there. We're also going to show you how to address these problems in a very straightforward manner. And then again, we're going to cover a family of papers who does that reliably, including my own paper with Brent Colloway, the paper of Sam Abraham, Jeff Udrich has a paper on this, Borusiak, Juravel, and Spears also have a paper on this. I'm going to briefly talk about the difference between these approaches without going too much into the detail about the differences. But my goal is like, well, how the solutions differ from each other. I'm going to highlight this is going to depend on some small tweaks, and hopefully you're going to leave this workshop with a better understanding of this topic. Finally, if you have to remember one thing from this workshop is that it's very easy to avoid all these problems that people talk about, difference and two-way fixed effects. We can embrace heterogeneity from the very beginning, right? And we still can identify causal parameters of interest. So the main message of today's workshop is that although everybody has this weird feeling about two-way fixed effect, diff-in-diff, the solutions are very easy. And they can be implemented in 2-3 lines of code, right? And we're going to go over all this as well. So this is a good point to stop if I have any questions, because I'm going to go with the canonical diff-in-diff. Before I talk about canonical diff-in-diff, let's see if there is any questions.
Pedro, there's a couple outstanding questions in the chat. So the first says, can we have a difference in differences design if we consider the untreated group before and the treated group after the intervention has been implemented?
So the answer is, I do not know if I really understand. We have to have a group. We do not have to observe the same units before and after the treatment. But we have to observe a group of units before the treatment and a group of units after treatment, right? So we're going to cover an example in a minute, right? In 30 minutes, where the units we observe in pre-treatment period are different than the units that we observe in the post-treatment period. However, they belong to the same group, right? So here, like in the example we're going to go through is like, in pre-treatment here is like being low earners, control group is being high earners. So as long as you are a low earner, and you know how to characterize if you are treated a low earner before or after, I do not need to observe the same unit. So but you have to have a group before and after, right? And group here is going to be kind of a big umbrella label that because we're going to compare before and after across averages. That's going to be important.
Yep. Okay, thanks. And then the second open one is, can treatments be turned on and off dynamically as well?
Yes, treatment can turn on and can turn off, right? In fact, let me go back here. In fact, that's this paper by the Charles-Martin and Dufay 2020. One of the key features of this paper is that it allows treatment to turn on and turn off, and it still do a difference and differences. The complication of treatment turning on and turn off, it is that it's sometimes hard to disentangle what is dynamics of treatment effects, right? And what is actually like instantaneous treatment effect. So in general, to do treatment turning on and turn off in a non-parametric manner, we're going to have to assume the maximum amount of treatment exposure, right, that is allowed for. So say, I only care about instantaneous treatment effect. So the only thing that matters for me is my treatment status today, right? So if I take a like headache pill, aspirin today, the effect is only lasts for today. That's a good situation when treatment can turn on and turn off. However, if treatment is training, if I give you training today, right, the effect of training persists over different points in time. It goes for tomorrow, the day after, so on and so forth. That is a situation when turning on and turn off is more complicated because things that treatment dynamics, persistence, and so there is a carryover effect. When you have carryover, things get complicated in the diff-in-diff world, right? So a lot of this is very clearly discussed in this paper by Deschamps, Martin, and Dauphin in the AER in 2020. And they also have a follow-up paper called Intertemporal Treatment Effects, right? Which they kind of like allow for additional dynamics. But the situation is much more complicated, especially in terms of interpretation.
Okay, and then a related question came up, sorry, just from that, on top of that last one. Can there be a setup where a particular unit may be treated and then the same unit at another time point is treated again? So there's multiple applications of the treatment. Yep.
Yes, so this is this can be characterized as a multiple treatment setup, right? So there is this paper by different scientists with multiple treatments by the same French team, right? That they allow for that. And I mean, in general, there is not much complication to do this. The question is, if you want to decompose what's the incremental effect of a dosage, that's the hard thing. Because if you want to talk about what is the incremental effect of treatment dosage, then you have to say, well, so suppose I take a treatment today and I take another dosage tomorrow. So in 2 days from today, the effect is because of the dosage 1, because of the dosage 2, or because of the combination, the complementarity of this dosage. So disentangle these effects can be complicated, right? And that's, I mean, you can do it, but there are some complications related to interpretation.
Great, thank you. Okay, I think we're good then.
Perfect. So we're gonna go dig into the canonical diff-in-diff because this is gonna set up the ground and give us the intuition of the basics. Once we understand the basics, we can take it away. You first learn how to walk, then you start running, right? That's the idea over here. So the canonical setup will also help us to set up notation, right? And when I say canonical setup here, it means I'm going to have 2 time periods only. Before treatment, I'm going to call it t equals to 1. And after treatment, I'm going to call it t equals to 2. And I'm going to have 2 groups of units only as well. I'm going to have group of units who are never exposed to treatment. I'm going to call those G infinity, right? So these groups are untreated by the end of period 2. And I'm going to have units who are untreated in period 1, but eventually become treated in period 2. It's going to be G2. What is important here that I have 2 time periods, 1 before, 1 after, and 2 time periods and 2 groups, 1 eventually treated, 1 never treated. You're going to look at this and say, Pedro, why are you introducing this infinity rotation? Are you nuts? This makes no sense. Why are you complicating things over? Why don't you just have like d equals to 1 and 0, so treated and untreated group? And the reason is that I want to introduce a general notation early on that I can stick to this notation throughout the whole session, right? To do this, what I'm going to do, this group notation is going to index the time in which a unit is first exposed to treatment. So 2 here is because this is the first time group 2, this group is exposed to treatment. G infinity here means like this group until the end of my panel, until the end of the data set that I have available to me, remains untreated. Why infinity and not a higher number? Because no matter how far you go, infinity is never going to be reached. So that's the idea here, to have like something that is very far away on the right-hand side. And to highlight potential heterogeneity of the potential outcomes with respect to treatment timing, the timing of adoption of the policy, right? We're going to index potential outcomes by G as well, this little g. So Y, little t, G, it is the potential outcome at time period T if units were exposed to treatment for the first time in period little g. So think about in this setup here, I'm going to have two groups only, two potential outcomes only. Y2, which is the potential outcomes for units at time period T if they were exposed to treatment for the first time period 2, and Y infinity, right, which is going to be the untreated potential outcome, right, if units remain untreated until the end of my data. So once we set up the notation, so I have two time periods and I have potential outcome notation, we're going to talk about what is the target parameter we are after, right? And in different setups, usually we are after some kind of average treatment effect, right? And the average treatment effect we are after over here, it is the average treatment effect among treated units in the post-treatment time periods. So what I mean by that? I'm going to define the ATT as the average of the potential outcome in period 2 in the treated state of the world among treated units minus the average outcome in period 2 in an untreated state of the world among treated units. So I break this parameter of interest in two parts. One that I have here in green and one that I have in red. The green component here is to say like, well, among units who are treated, right, in the post-treatment period, I'm going to be able to observe the treated potential outcome in period 2. So if you are treated, I do see a treated outcome. So this first component here is going to be fairly easy to identify and uncover from the data. This is estimable from the data. The name of the game we're going to be playing, it is, well, among units who are actually treated, no matter how much data you give me, I'm never going to be able to observe their untreated potential outcome, right? So for treated units, I see treated potential outcome. I do not see untreated potential outcomes. So this is going to be the counterfactual component we're going to be trying to uncover from the data, but the data itself is not going to be sufficient for us. So what we're going to do, we're going to have to make assumptions that are going to allow us to impute this red component. So everything about difference and difference is like how we're going to uncover, how we're going to impute this red component here, this counterfactual component which measures the average untreated potential outcome among treated units. So again, causal inference is not black magic. We're going to have to start owning our assumptions to uncover that, right? There are three key assumptions we're going to be making here in difference and differences. I have them in ugly slides, but I'm going to try to explain this in English, in plain, so everybody can follow and assess if this is plausible or not in their application. The first assumption, it is called Sutva assumption, so it's stable unit treatment value assignment, right? It's essentially an assumption that is my outcome only depends on my own treatment, right? So essentially, if you are treated, I observe treated potential outcome. If you are untreated, I observe your untreated potential outcome. This assumption rule out general equilibrium effects. This assumption rule out network effects, spillovers, and many other things, right? This assumption is like, it's not without a lot of generality. And essentially what this assumption is telling us is that like, well, in order to map potential outcomes to realized outcomes, we're going to have to rule out some of this interference. And this is not about difference and difference in general. This is about potential outcomes notation. So this assumption is essentially hidden in every potential outcome notation. It can be difference and differences, RDD, it can be like unconfoundedness, instrumental variables, and so on and so forth. My goal here is to say, we're going to own it. We're going to explicitly say, and once you say like, well, what happens if I have interference, right? This means that you're going to have to choose the unit of analysis I here very careful. So if I am worried about spillover effects in classroom, right? What I can do, I can analyze, like if I care about education attainments, right? I'm going to look at data at the school level. Oh, but I'm worried about spillover between one school and another. I'm going to aggregate the data further and analyze things in, like, I don't know, district level, and so on and so forth, right? So the choice of the unit I here plays a crucial role on how important these assumptions it is to be violated or not. But again, there is not much we can do right now in difference and differences. There is a very rich statistics literature emerging about how to address SUTVA violations. And I encourage everybody to search causal inference with interference on Google, and you're going to see a lot of fresh new papers trying to address this issue. So SUTVA, check, that is submitted. What about the other two assumptions, which are more particular to difference and difference? The second assumption, it is a no anticipation assumption, which is telling that before treatment happens, units do not act on the knowledge of the treatment date. So essentially it's telling, if I am not exposed to treatment yet, I'm going to behave as if I am untreated, right? So if I tell you today, like, Brady, you're going to be treated in 10 days from today, right? Brady looks at me, what? Pedro, if I'm going to be treated 10 days from today, I'm going to start changing my behavior today, right? Because I'm preparing for my change in treatment status. If that happens, the assumption is violated, right? So if units, if individuals or entities act in anticipation of treatment behavior, of treatment assignment, this assumption is violated. So this is in general not without of law of generality. This is going to be important here to define what is actual treatment time. Is treatment time the time of enabling the policy, or is the time of the policy announcement, right? So depending on the way you define treatment time, this assumption is more plausible or less plausible. Again, this is going to vary from application to application, but it's important to recognize this assumption. It is important for us. Very often, people do not talk about non-anticipation assumption because it's very easy to bake this assumption into our notation. We're not going to do that. We're going to make it explicit. We're going to screen to the word so people can actually see if this is something they believe or if they do not believe. So the final assumption, it is about parallel trends, which I mentioned a couple of times already. And this is essentially what, in my view, like defines a difference and difference type of analysis. Non-anticipation, for example, anything that has to do with time requires non-anticipation. Non-anticipation is very popular in time to event analysis, duration analysis, right? They also need the same assumption because non-anticipation about treatment timing. But what characterizes differences and differences, in my view, is the so-called parallel trends. And the parallel trends here states that in a state of the world, when treatment does not happen, so I have only y infinity over here, only untreated potential outcomes, what I'm telling is that, like, the average evolution of the untreated potential outcome among treated units, it is the same as the average evolution of untreated potential outcomes among untreated units. All right, so what I'm telling is, like, if treatment did not have happened, these outcomes, the average of these two groups, the average outcome, the average untreated outcome for these two groups would evolve in parallel. And I'm not telling they have to start from the same point. This is crucial here for us. They can have different starting points, right? So they don't have to be similar in levels, but they would have the same growth over time, the same type of trends. So that's the idea of parallel trend assumption, right? And once I own,
Pedro,
yes,
sorry to interrupt
yes,
again. A couple questions just came in about these assumptions. First of all, just in general, and you may be getting to this, so feel free to say that's coming up. Are these assumptions testable empirically?
So SUTVA, I mean, you can, if you maintain SUTVA and no anticipation, right? And you have more than 2 time periods, some version of the parallel trends, it is testable. In the basic setup, when I have only 2 periods, right, one before, one after, none of this is testable. All this has to be believable. Now, if I have several pre-treatment time periods, I don't have t equals to 1, I have t equals to 0, t equals to -1, t equals to -2. I have many time periods before treatment takes place. As long as I maintain SUTVA and no anticipation, I can test parallel pre-trends. But this is not exactly the same as parallel trends in the future, right? It's only parallel trends in the past. But in general, that's a good indication that our assumption it is plausible. This is not always the case. It's going to depend on the situation. If your environment has changed so much from the past or not, but think about in economic history. If I look from data from 100 years ago, and I do not see things in parallel over there, is that actually informative of what are going to happen today? I'm not sure, in my view. Right, so I come from a camp that looking for parallel pre-trends can be informative in some environments, but in other environments is not really informative.
Okay.
When I have, so when we have variation in treatment timing, which we're going to go over next, some of these assumptions are directly testable, some are not. Right, so in the simplest case, without variation in treatment time, all I can do is look at the past and see if the assumptions are plausible. It's a kind of pre-test.
Okay. A couple related to parallel trends. So first of all, why not define parallel trends in terms of rate of growth? So dividing each side by its expected value at time 1.
So this is a good question. I mean, so in this way I'm doing it, I'm not taking a stand on how you measure the outcome, right? So if you measure the outcome in levels, this is the outcome in Y levels. If you measure the outcomes in logs, right, this can be a ratio, is the expected value of the log ratio, right? So in general, the way you define your outcome of interest, your Y, will have a direct implication for the parallel trends. We're going to talk about this in like after the exercise as well, because this is important. And why not take the ratio of 2 conditional expectations, right? And you can do that, actually. This is not going to be a differences in differences. It's going to be like a ratios in ratios type of analysis, but you can build on the same intuition to do that. It's just not very commonly adopted because that introduces non-linearities.
Got it.
But it's definitely possible.
Okay. When treatment can turn off and on, can any of the difference methods be used when there's possible reverse causality? And again, any of these questions, if you're going to touch on them, just say we'll come to that. Yep.
So in general, no, you cannot do it because that's going to violate parallel trends.
Okay. Are we estimating?
When treatment turn on and turn off, you're going to have much stronger parallel trend assumption than these ones. Right? That's a caveat. The assumptions are different.
Okay. A couple related questions again to the parallel trend test. So the parallel pre-trend test is a test for anticipation, correct?
It is a joint test of anticipation and parallel trends. It's the 2 of them at the same time, right? And it's possible that I have violation of no anticipation assumption, I have violation of parallel trends, and this violation is going opposite direction. The things look perfect in the past, but they're very off. Right, so that's why when I was telling, as long as you maintain one, you can test the other. So if I believe parallel trends hold, right, I can test for non-anticipation. If I believe non-anticipation hold, I can test for parallel trends. If I'm unsure about the 2, I'm going to test jointly the 2 assumptions, and it's not the violation of the 2 assumptions can offset each other, so we have to be very cautious about that.
Okay. A couple more came in. So are we estimating late if we assume SUTVA? So since late is the effect on the compliers and SUTVA implies there are only compliers.
So not really. So here, what you're going to be estimating is the ATT, right? Is the average treatment effect on the treated, right? SUTVA going to allows me to map potential outcomes to realize outcomes. SUTVA is doing only that. right? I have potential outcomes mapping that to realized outcomes. So it's a kind of a switching equation type of map. If I do not have this restriction, I only want to have potential outcomes and I do not know where they live. I open my window, I don't see them running around. So one way to discipline what I want to measure and what I actually see, it is to introduce this assumption. That's the idea over here.
Okay. Is it more likely that parallel trends hold with similar levels as Lang and Lang in 2020 would argue?
Yes, I mean, if you ask me, the dream world is that they have the same levels, right? So it's much more appealing. If they have the same levels, you don't really need differences and differences, right? They have the same starting point. So in those situations, I mean, if they have the same levels, this outcome over here, it is the same as this outcome over here. So you can cancel this out, right? So what I essentially going to do is like a pre-post. So if they have kind of the same levels, it's where this is going to be more plausible in general. Also, parallel trend assumption is much more plausible when the pre and post period are nearby, right? If the outcomes are 1 year apart from each other, this is more likely. If the outcome is 20 years apart, it's harder to work because shocks can hit things differently. So there is a periodicity as well here that this is more plausible than others. We allow for long run effects. We allow for things in the long run, but the assumption becomes stronger as you go over time.
Okay. And last one for now, and then we can move on. To follow up, if I was going to write a paper using diff-in-diff and I wanted to justify that the assumptions are reasonable in my setting, what would be considered sufficient to make that argument? Would parallel pre-trends be the gold standard, or what would typically be the language one would use?
So in general, I mean, this is a tricky question, right? I'm gonna give an agnostic answer on the way I see people actually using it, arguing, right? Essentially, we're gonna have to argue the treatment timing is kind of quasi-random, right? You're gonna look at pre-treatment trends to see if there is no pattern over there, right? And you're gonna also take a look in somehow if the treatment mechanism, if you have context-specific knowledge, how people sort into treatment. If treatment is a decision, right? I choose to be treated. Right? I choose to enroll into training. It's harder. Then if the state enrolls in a policy, enact a policy, this is more plausible. Because I mean, so that is a kind of who is taking the decision? Is this an outcome of my own choice or not? Right? But in terms of data, I would say the gold standard, it is for looking for pre-trends. And I would say if you want to really justify this, do sensitivity analysis. Look at potential violations of parallel trends and leverage those potential violations to inform potential violations in the future. And in the bonus, I'm pretty sure I'm not going to have time to talk about that today, but there is a bonus session of this slide at the end when I show you how you can actually do that. There is software implemented for that. This is based on a fantastic paper by Rambachan and Roth, 2022, on a more plausible approach for parallel trends, right? Which they discuss how to do sensitivity analysis to validate this. To me, that is the best you can actually do.
Great. Okay. For the other questions, I think we're going to move on for the sake of time, but hopefully we'll come back to these other questions live at the next time of pausing. But I want to make sure that Pedro can get through the relevant material. So
perfect.
We'll come back to this. Yep.
Thank you, Brady.